this is
And so far, the previous work I presented are to find the interpolation point. We do not care about the mathematical function of the original data. So what we need is the interpolation value. We do not care what is the function we need for it. So now I will talk something different. Now we are interested in not only the interpolation result, but also the function. So I will start by talking about polynomial fittings for given data. And then we should consider least square fittings from the data. And the rest of the parts are from another topic, which is called function approximation. If we have already a function, how can we approximate another simpler function? For instance, we can approximate it with a rational function like this, where n and d are polynomials. We can use this kind of function to approximate a given function. So there are two problems presented here. One is how can we find the fitting function from the original data? The other topic is how can we find a similar approximate function for any given functions? So there are actually two topics I want to present in this section. First, we can consider how we can get a function, a polynomial function from the existing measured data, sample data. And the function call is quite similar to inter P1, something like that, where we have measured the data sets x and y, and we can specify a degree for polynomial. Then we can get the polynomial. So let's see how can we find the polynomial and what is the difference between polynomial fitting and the interpolation problem we talked earlier. So let's consider this function again. Why we can use a polynomial? It is known from Taylor series expansion that any function can be expressed by infinite sum of polynomials. And here the topic is, how can I find a finite term polynomial to fit the original function? Suppose the function is given like this, and we again can generate data from the function. And then from the data we can find a polynomial to fit that. So the function we are using is to generate data, and then we can have a third order polynomial. Actually, we do not need the last command. So we can generate data first, and we specify 3 here, and by the coding of polyfit, we can get a polynomial. And the result will be the coefficient of the polynomial in descending order. So it should read something like 2.84 x cubed plus minus 4.7 x squared, something like this. So by the use of polyfit function, we can easily obtain a fitting polynomial. So now my question is, what will be the result of how well does this polynomial fit into the original function? So by comparison, we can specify another x vector with smaller increment. In this case, we can have y1, and x1 and y1 are theoretical values, and x0, y0 are the sample points. So So what about the fitting? What about the interpolation result? If we do it like this, we can have Polyvale function, and we can have P3, and then we can place x1 here. This should be the result if we substitute the x vector into the polynomial we obtain. So now we can compare the difference among them. So the command we use is plot x1, y1. This is the theoretical result. x1, y2, which is the fitting result, and also x0, y0, the sample point. So we can use a command like this. This is the result. And the blue ones are theoretical results, and these are the fitting points. Unfortunately, when the polynomial, when n equals to 3, will not get a good approximation to the original problem. So to get a better fitting, we must increase the value of n. And perform evaluation again, and then we can draw the plot. And the result is better. However, it is not as good as the interpolation method when we use piecewise cubic functions. And also, it should be noted that the fittings around the boundaries are not quite good. If we further increase the degree, for instance, to 8, you get the fitting results, and also you can compare them, and it can be seen that the two are very close. So you can fit the original function or original data point by an 8th degree polynomial. It should also be noted that when the degree of the polynomial increases, there must be large coefficients. And if you select an even higher degree of polynomial, you may find even larger coefficients, which may cause numerical instability. So we must not select the degree too high. If the fitting result is satisfactory, for instance, in the case for n equals to 5, we see that the original one and the fitting one are quite close. We can use that one instead. Normally, we do not have to select the order of degree too high. So let's go back to the 3-degree polynomial again, and let's draw the results. So let me show the difference between interpolation and the polynomial fitting or other function fitting. The difference is that for the sample point, if you are using interpolation as I talked earlier, the sample points are on the fitting curve. However, if you use a function, those points are not necessarily to be on the curve. So these are the difference between the two methods. And if you are using a function approximation, the best thing is you can find the function itself. And if you are using interpolation, normally you do not have a function. So these are the difference between the two methods. And you must be very careful in choosing the degrees. And now the question is, for a normal problem, the function is not given. fx is not given, so you cannot compare the fitting result with the original function. So the question is, how can we choose a value of n? If the function is not given, we can solve the problem in this way. This is slightly different as your question to the interpretation.